let's see what kind of solutions we have to our new complex dispersive wave equation. Let's guess an EM plane wave, which is like guessing a traveling wave, where we would say E and R and T is E naught, and just, I'm going to make it easy on myself, I'm going to assume that it travels in Z, so KZ minus omega t, and it's in, say, the I hat direction. So we aren't going to do the full general three-dimensional problem. For what we're doing right now, there's really no point. So let's just do it that way. If we do that, the del squared becomes easier. It's just a second spatial derivative. So let's plug this in. So del squared of E just means d2E dr2, and it only depends on Z, so we're just going to write that as we pull out, let's see, take two spatial derivatives with respect to Z, so two J's come out and two K's come out, and two J's make a negative sign, so minus K squared E naught E to the J KZ minus omega t. And let's see, that equals, and then we had this big mess, 1 over c squared times this big thing, 1 plus n e squared over m epsilon naught omega naught squared minus omega squared plus j gamma omega. I think that's all there. And all that times d2e dt 2. So let's see, two derivatives is going to bring out a negative j omega. It's going to do it twice. So that's going to give you a negative omega squared e to the j, I'm sorry, e naught e to the j kz minus omega t. Okay, so that's what the wave equation tells us. So let's see, the E naughts can go away, the oscillating part can go away, and well, that's about all that can go away. We can make them both positive. That make us feel better if we do that. And we get that, let's see, if we bring this over here, that omega squared equals k squared times this thing upside down, c squared over this thing. So we could write it like this, so we take the square root, that omega equals c over the square root of this thing, 1 plus ne squared over the mass of the electron over epsilon naught times omega naught squared minus omega squared plus j gamma omega times k. So this is our dispersion relation. For plane waves in empty space, no dielectrics or anything, it was just omega equals ck. All waves go at the speed c. All light waves go at the speed of light. Now we have it in a form where it's usually written omega equals c over something k, and that something is the complex refractive index of refraction. So the complex index of refraction. And it's equal to this thing under the square root, right? So n tilde, tilde means it's a complex number, equals that thing. Okay? So n tilde has complex, has a real part, n real plus j times n imaginary. So, and it doesn't just fall apart into the real and imaginary part, right? I mean, it's a square root, and then the imaginary part is part of a sum in the denominator of something plus something else. I mean, you know, it's not just real and imaginary is not obvious, but both parts are there. It has a real part and an imaginary part. This index of refraction you may be familiar with. You've heard that term before. You may be familiar with this as, you know, the index of refraction of glass is 1.5. Of water, it's 1.3. It's what makes light slow down when it enters a medium. It's what causes light to refract and bend as it enters a medium. We'll be talking about that later. So this is that normal index of refraction they're used to thinking of is just pointing out it can actually be complex. It can have an imaginary part. For glass and other dielectrics, that part is very small. The imaginary part is teeny, but in principle, it's there. So now we'll look and see how does light behave if you give it this complex index of refraction.